Okay, so today's lab we're going to do, or this week's lab, we're going to do kinematics. So what you want to do first is that you log on to Canvas and click on modules. And then scroll down and you'll find the kinematics. So click on that PDF file and then so I'm going to click on that and I'm going to share my screen again about this. All right, so kinematics. So basically, kinematics, refers to when you have an object moving under acceleration, so the velocity would change, and the displacement would change, and the equation one through three, provide the informations about how each quantity is related to each other. So you should be very familiar with those three equations. So first equation relates the initial position to the final position with this equation. So you have the initial position plus initial velocity times time plus 1/2 at squared. And this will give you the final position. And the second equation is that final velocity is equal to initial velocity plus acceleration times time. And the third equation is that acceleration is a constant. So for constant acceleration motion, these three equations are the equations of motion that describe how the object changes position, velocity, with time, okay? So the objective of this experiment is that given a scenario, we're going to find the acceleration from three different approaches. So in this activity, it actually has two different cases. Case one is for the level, when you have a horizontal, when you have a track that is placed horizontally, and then you push a car, and then the system is going to record position and also time and velocity, and then based on the information, you can find the acceleration. However, we're not going to do the level case. We're going to be just doing the incline. So the incline, we'll have the setup like this. So I'm going to scroll down. So this is the incline. So basically you have a track, and then we're going to raise the track. So we'll put something under the track. So it's going to make an angle with the horizontal by angle theta. So, and the height of the object that's placed under the track, you can measure that. So this quantity will be given. So this is the h, and then you're going to measure the length of the track from this point all the way to where you place a sensor. And this sensor is what we call a motion sensor, and the motion sensor is connected to the computer. And once you release the card, so this is the card placed on the track, and then once you release the card, the system is going to measure time, measure position, and measure velocity. And based on this information, we can deduce the acceleration of the car. So when you have a car, let's say you start from before you release the car, you will have the car placed at the on the right end, and then when you start the program, then when you hit the record button and release the car is going to it's going to slide down, as we know, because of the gravity. So it's just going to slide down, and it's going to move at a constant acceleration. So theoretically, the acceleration is this, can be found by using this equation. So your A, the acceleration of this car is equal to g sine theta. So it's not just the gravity, it's actually one component of the gravity along the track, or the component of gravity that is along the track is the acceleration. So you have the g, which is 9.8, and sine theta is the other component. If you know your vectors, you just resolve the vector into the x and y, and a is the one of the component of g that is along the track. And so you have 9.8, and what about sine theta? in order to know sine theta, remember just based on this geometry, we know that you have the h here, you have the L here. Then you can just based on this, so approximately you can say that this is your L and this is your H. So to calculate that the angle theta, for the sine of theta, you would just use the H, which is the height, and over the length of the track. So in other words, you don't really have to measure theta because the theta is so small. If you just use a protractor to measure theta, you're going to get a large error. So instead, we're going to use this geometry to infer the theta. In fact, we don't even need to know the information theta because ultimately it is the sine of theta that we want. So you can just use 9.8 and then you have the H, you have the L, and then just multiply that and you get your value of A. And this is your theoretical value of A, which you're going to use the experimental value to compare to this theoretical value, okay? And like I said, theta, you don't need the information of theta. And when you use this equation to calculate your A, remember that everything has to be consistent. If this height is given, everything, you convert them into meters. So height in meters, length of track in meters, then you'll get your acceleration, okay? So this is basically experimental setup. And then how do we use, so based on this, we know that when you have a car that is sliding down the track, it's going to have the acceleration, it's going to have a velocity changing with time, and the displacement is also going to change with time. So if you go back to equation 1 through 3, you can see that you have this various various equations. So we're going to utilize each one of them. So going back to this, so we have the acceleration, and we want to use the equation to find out how do we deduce the experimental value of the acceleration. So you have the position, final position is equal to initial position, and then plus initial velocity times time, and then plus 1/2 AT squared. Okay, and because the whole thing is starting from rest, so there's no initial velocity, so this goes to 0. Okay, so what you have here is that you move this to the other side and take that as d, this displacement. Then you have the d that's equal to 1/2 AT squared. So this is actually very similar to the lap 2 activity. Okay, except that the lap 2 is the free fall, and this is along the track. All right, so you have this. So the program is going to measure d. The program is going to measure time. Okay, so you need to in order to find the slope, in order to find the experimental value of A, you will plot d in the vertical, in the y, and then over 1/2 t squared. Okay, so by the way, the displacement is not proportional to time. It is proportional to t squared, as this equation shows. Okay, so you have the d versus 1/2 t squared. As you can see, when you plot d versus 1/2 t squared, then the slope is going to give you experimental value of the acceleration. So this is one plot. You should have one plot that is d versus 1/2 t squared. And the second equation, let me just scroll down because I need more space. And the second equation is v is equal to initial velocity plus at. So again, because the car is released from rest, so there's no initial velocity, right? And then the system is going to measure velocity, is going to measure time. So based on this, we're going to plot velocity versus time. And here you can see that you can say that velocity is proportional to time because it is proportional to just the t, not just t squared, okay? And so when you do that, the slope is going to give you the experimental value of acceleration. So from the graphs, you would have one slope from d versus 1/2 t squared, and you have another slope that's from V versus T plot. Okay, and you're going to enter those information in the table. And in the third approach, so I label that as approach 1, approach 2. The third approach is that the system also measures acceleration. Now acceleration, because this being a constant acceleration, so you don't need to do acceleration versus time. You don't need this plot, okay? What you need is that based on the acceleration value, find the average and also find the error, standard error. That will be it. So altogether, 2 figures. One is this, and the other one is this. And then you're going to use the acceleration, just find the average. Use Excel building function to find the average of the acceleration based on the acceleration data, and then calculate the standard error. Okay. Sorry. So let's go scroll down. So let's look at what you have here. So the height, as I mentioned, height of the object will be given, the length of the track will be given. So based on this information, you can calculate theoretical value of the acceleration, and that whatever value that you calculated here, you should put it back here, because that is for the incline. Okay, we're not going to do any level case, and then and then for the average, this is the one that's from Excel. When you do the calculations, you can find the average acceleration, and then remember to include the standard errors. So it's whatever value of the average acceleration plus or minus the standard error, and then you're going to compare. When you do the comparison between the average acceleration and theoretical, find do the percent error of this too. So when you do that, you can ignore the standard error of this average acceleration. This standard error of the average acceleration just refers to what the error associated with this set of data. Now the percent error is the one that we want to find comparing these two quantities. Okay. And then you're going to get the slope from the d versus 1/2 t squared plot. That is one acceleration. So you're going to compare this acceleration. You're going to compare this acceleration to this theoretical, to get your percent error. And then same thing for the v versus t versus time plot. You're going to get one slope, and then that slope you're going to compare it to the theoretical, to get your percent error. Okay, so basically, this is what you want to do for this lab. So let me stop sharing for the moment, and let me open up the Excel file so that you know. So the data file. So the data file. Let's come back to Canvas. The data file will be right here. Go to the lab data, click on Kinematics data. This is the Excel format. So you can just download that Excel file and work from there. And then I'm going, after I finish this recording, lab 3 instructions recording will be placed under this this subfolder. So let me bring up the Excel file. So the Excel file, once you download to your computer, that looks like this. So the time information is given, and the displacement is also given. So based on this, remember, because from the position data, you want to plot d versus 1/2 t squared. So you need to use this. You need to use this time information to calculate 1/2 t squared. Hopefully you still remember how to do the 1/2 t squared, because that is the one I show in the lab 2 instructions. If you forgot how to do this, just go back to lab 2 instructions. Then you'll find how to do the 1/2 t squared. And once you have the data, then you want to do d versus 1/2 t squared plotting, and then you'll be able to find the slope. Now for velocity, the time and the velocity data are given. So you can just plot velocity versus time. So you can see that we have tons of data, and then just select the data that, under the appropriate column to do the plotting. For the acceleration, you can see that we have time, we have the acceleration, and you get a whole bunch of data, right? So for the acceleration, I do not want you to do the plot because the slope of the acceleration versus time plot will be 0. So you're not going to get slope from the acceleration versus time plot. Instead, you want to use this data, and then you want to do the average. So based on this average, select the data on the under the acceleration column and just find the average. Use the built-in function to do the average. And then, and in addition to that, you want to calculate the standard error of this set of data, just to see how far, are the data very close to each other, or are these data points are actually all over the place. Okay, the standard error basically is the indication how constant this acceleration is, and then the L is given here and the H is given here. They are both in centimeters. And based on this information, you can calculate the theoretical value of the acceleration. Okay, so that's basically what you want to do today. Okay.